Hello, can I add something here? Can you hear me?
Hey,
Hello?
do, Ron. Please do.
Yeah, okay.
Nice to see you here too, by the way.
Okay, hi, Tim. Yeah, three things. What I wanted to mention, are you familiar with the work of Colonel Rex Schleicher and his patent on nonlinear electromagnetic systems? No?
No,
No
not
one's,
yet.
okay, a friend of mine, the patent, he was living in New Mexico, but the patent for Colonel Rex Schleicher NEMS, you can find that at Rex Research, nonlinear electromagnetic propulsion system. It was Air Force funded. I'm not even sure it's even open to the public anymore because what it does, if you look at the NEMS patent by Rex, REXSCHLICHER. It's an easy find. It's about 15 years old. In my conversations with Rex, he talks about, are you familiar with the word cryogenic aluminum? There's a term called cryogenic aluminum. And a cryogenic aluminum is on the verge of superconduction, but not at super cold temperatures. The next item I want to bring up, when Paul Murad mentioned copper, I guess people are familiar with the Wallace patents. The Wallace,
Yes, indeed.
Yeah.
the Henry Wallace patents. What he is looking at, Henry Wallace was a friend of mine. When I was at Villanova, he was working at General Electric Space Flight Systems in Valley Forge. And we didn't know it at the time. As I was going to Villanova, he was driving to Valley Forge Space Flight Center. And he has two patents, 3626605, 3626606. The patent was distributed because there's two technologies there. Hank Wallace, which can be found by rexresearch.com. There's also a neat introduction by the new scientist at the 10th anniversary of the Wallace patents were patented in 1970. Oddly enough, Valentine's Day, February 14th, 1970. And at the 10th anniversary, the British publication, The New Scientist, they had an article on, it's at Rex Research, they had an article on Wallace's patents, and it says the military was very upset that the patents were issued. It's all there at Rex Research, but the whole crux of the Wallace patents, which may be pertinent here, is he talks about when you get above, when you have lightweight metals, your number of protons must always equal the number of electrons. You can have less neutrons. When you get above copper, like when Paul Murad mentioned copper, if you look at the periodic table, and you'll see that heavier as you go to U-235 and so forth, you get excess neutrons. And so the candidates for the spin polarization of neutrons within a metal happens at metals above copper. So in terms of being a Wallace effect in aluminum, you won't see that. But as far as being above it, that's okay. I mean, you can get there. And but that's largely it. There's a third item I wanted to mention. I got beyond myself. Rex Schleicher is interesting. Wallace was also fired. He was fired from General Electric, Valley Forge Space Flight Systems, and his friends. Wallace did a lot of energy-saving patent research for GE. He was a notable contributor. I looked up the list of his patents at one time, and he dated. His friend said, if you keep doing gravity research at the GE, they're going to fire you. And he laughed. He says, no, they're not going to fire me. And he was fired. He was terminated. As you know, Alzofon, and I know some people who like to remain hidden from Alzofon, but they got to survive Boeing after Alzofon. And then there's also Chekhov that I follow, and he uses the aluminum disc. And so in terms of the inner relationship, Chekhov of Russia, which I don't know is valid or not, but this is just, but cryogenic aluminum is unique. Also the work of Alzofon ties to this, but it's metals that are above the weight of copper. Oh, also the third item was on the McCandlish ARV. Everybody with me? And yeah, the bottom part of that, the dielectrics in there were quartz. The quartz comes in a chiral variety. You have alpha and beta quartz. There's a certain orientation to them.
Ron, sorry to cut you off.
Ron, I had talked to Mark McCandlish, and he specified to me when I asked him about what dielectric they used in those bottom plates that it was Herkimer quartz that they had specifically made by GE, no less.
Yeah, well, Herkimer diamonds. Are you familiar with Herkimer diamonds?
Yeah, we looked them up, and they have interesting dielectric properties and piezoelectric properes.
Yeah, like I said, quartz comes in chiral varieties. Type in alpha and beta quartz. And so in terms of the ARV, I really don't have much problems with the ARV. But like I said, in terms of dielectrics, also deep in my files, I go way back. I'll give you a brief insight. Does the name Redford mean anything to anybody?
Ron, getting back to the quartz, do you know any place where we can purchase the correct kind of quartz? And just repeat again what kind of quartz it is.
It's Herkimer diamonds. Herkimer diamonds is found in
Herkimer, New York. There's a campground there. You can actually pay to and mine the diamonds. I've gone there. Go out to the field and mine for diamonds there.
You could probably road trip it. And because I looked online to buy some, and not as though I need them. Because at one time I was looking that I came across the patent. This goes way back into my files. I have about 100. My law was I could not have the number of ring binders exceed my age, but now they're up to 100. So the limit is 100. But in my files, there was a Russian patent, and it was on a material that was polarized that used a glass material, and it was a Russian patent. And the Russian patent, oddly enough, wound up in a company in Dayton, Ohio. And for security, the plant was located on the flight path of Dayton International Airport. And so in terms of having, I don't know if the Russians were trying to do something with glass, and there was no mention about propulsion. It was just a unique material, but the number of Russians on it were staggering. But anyhow.
Ron, can you put these things on, and can you put this quartz on sheets?
Well, a quartz is glass. I mean, you're talking about the. Okay.
Because I keep looking at, something like this, like.
Yeah, I mean, you can roll it. I mean, quartz amorphous. The only thing is with quartz, the advantage of chiral quartz is by having chirality, you have handedness and you can polarize it. I'm not sure if conventional glass has anything. I mean, if you're going to polarize something, you need a dipole moment. And by virtue of having a dipolar, you have a thumb, you have a dipole moment.
Yeah.
You put that electric field and you're getting orientation. And so
the thing in looking in the ARV, what you're doing is you're concentrating one of those poles at the center and you're diffusing it all around the edge of the thing.
Yeah.
So you have what you're suggesting.
So, yes. So anyhow, like I said, in terms of where to work, if you can make a trip to Herkimer, New York, might even be on the thruway. I'm not even sure. But you can get a Herkimer diamonds for free. I looked at them, I'm buying them online, and for the price of them, I go, oh my heavens, if you live in Jersey, go up there and get a bucket full and come back, melt them. And I mean, if you want to do something that's ARV-like, myself, I got enough stuff to do. But anyhow, in terms of encouraging others, I just want to give people directions of where they could go. Also, in terms of Alzofon, does anybody know about the Penn State connection to Alzofon? The material science people, according to my sources, all this information that I say here is subject to a disclaimer that I may or may not be correct. It's the disclaimer. Anyhow, according to my sources, the Alzofon material was made at Penn State University, and since it was Penn State University, it may have been the Rustum Roy Laboratories. And I see a friend of Tania Slawecki was here. But anyhow, the material was not a solid. It was a nano powder. according to my sources. And when you're dealing with nanopowders, you must keep them under nitrogen atmospheres. When you get down to metals at very, very small diameters, by virtue of the surface area and oxygen, they will explode upon contact with air. So in terms of dealing with Alzofon and sheets and stuff, even I wouldn't use inclusions. If you have a way of getting to nanopowder aluminum, give that a try. Also, in terms
what type of aluminum, Ron? What type of aluminum did you say there?
Nano.
Nano pattern.
And that's it, now. Mark is holding up and actually, yeah. So Mark is holding up a bag.
Yeah.
That this is the finest aluminum powder we have. It's 5 microns a piece, 3,000 mesh.
Okay, I'm not sure. 5 micron. Okay. Like I said, in terms of what was made, I know it was made. It was custom made. Fred Alzofon did not pay for it. That's all I'll say. It was done by one of his business partners. And when they split up, the business partner took the powdered material. And so that's all I can say.
Like I said, it was destroyed by ego.
Yeah, well, yeah. Well, anyhow, I want to just go back a second. I knew there was something called PACE, Planetary Association for Clean Energy, held at the University of Toronto, October 1981. And it was one of the Woodstocks of anti-gravity, as well as Paul Murad's MITRE Corporation 2003 high-frequency gravity wave. But anyways, at the University of Toronto, we had about 10 copies of Alzofon papers, and we were staying at the Hotel Windsor on Windsor Street in Toronto. And at 1 o'clock in the morning of the first day of opening, there was a fire alarm. And we all went down to the bar. The fire alarm, the fake fire alarm, we were held there for an hour. We didn't realize till next morning, but people who had the Alzofon papers were stolen from them. And yeah, it was an AIAA paper, and we have no idea why anybody, but other items were stolen were stolen. But the people that I were with were people who were supporting Alzofon, and we were wondering why on earth would they go through our belongings? And they stole Alzofon till they got in the, I don't know how many were involved. Somebody said it had to be the government of Canada or something, but why they would steal a paper that was published. But they also looked for other things. And when I was coming back through security I crossed at the Rainbow Bridge at Niagara Falls, and for some reason they singled me out. I told them I was coming back from the University of Toronto. They said, "Are you bringing any experiments with you?" And I said, "Well, no, I'm bringing nothing back with me." But it was an odd question. Why would they?
Well, Ron, let me mute you for just a sec, and let me go back to Mark here for a second.
Okay, I'm finished here. I'm good.
Okay.
So,
okay. Sorry about that.
Actually very, very interesting.
Okay. Well, and that was my worry was that we weren't going. I wasn't sure if we were going off track or not. Do you want me to unmute?
No, that wasn't off track at all. Actually,
I know Wayne had a question too. Wayne was waiting to ask a question.
Oh, yeah, Wayne, what's up? Wayne is also working on Alzofon.
Yeah. So I have a question for Ron, but first because we're talking about Alzofon, I'll just show some of my my earlier the stab I took at this. Let me just flip my camera around here. So this piece right here, these are 2 microwave oven transformers, and what I did is, this is my attempt to make an electromagnet to get in that range of about 3,300 Gauss, which I did achieve. And then I hung my samples down there. But I wasn't able to get to the point where I could control the magnetic field very precisely. And then I was using this gun oscillator, but I wasn't able to make sure or check that it was actually emitting the microwaves. And this one here is rated for 9.4 gigahertz. So I got lucked out with this. I found a marine radar at the side of the road. And so I was basically trying to shoot it here at the sample. And then I was pulsing this at about 6 millisecond pulses, as Fred specified in his paper. So, and my results were inconclusive, and I made a YouTube video about the whole experiment. So I just wanted to share that since we're talking about it. And I have another setup on my bench here, which is kind of a variation on the concept. But I'll go into that a little bit later. And then my question for Ron.
How heavy was that device? How heavy is that device you're showing us right now?
This?
Yeah.
Well, these are 2 microwave oven transformers, so they're pretty heavy. This is probably 40. Oh, I don't know, 30 pounds.
Yeah, it looks heavy. And there's a piece of metal behind it. What is that? Is that iron or steel or?
Oh, well, Ron was talking about the Wallace patents, which I wanted to ask. I had a question about, and I did kind of a study on Wallace's patents and his kinematic field generator and all that. So he talks about when you rotate brass or any metal with atoms that have a nuclear quantum spin number or a net spin. Basically, atoms with an odd number of protons in their nucleus have a net spin or a magnetic moment. So when you spin it, the idea is that the nuclei will polarize. And he talked about something called a kinematic field, which is related to the idea of gravitomagnetism. And he differentiated this field from the magnetic field in his experiment. He was able to, through his apparatus, to eliminate the possibility of, it's just magnetism, plain old magnetism, because this field, I don't know if I don't know my audience here. I don't know if you guys how familiar you are with it, but so he was able to detect the temperature change in a sensor, and he explained it as being, so as the nuclei polarize, there is a decrease in entropy, and so it behaved a little bit like a heat pump. So the degrees of freedom are lost by.
Is this the Unruh effect? UNRUH effect?
I can't say for sure. I think it might be related from what I've read about the topic, the concept of lens thirring and gravitomagnetism or gravito-electromagnetism, frame dragging. All those concepts seem to be related, and astrophysicists believe that it exists, and they observe it in cosmic bodies, like really large bodies in space. But where Henry Wallace was really, I guess you could say, innovative was in considering what's happening inside the atoms, because you have the nuclear mass there, and it has angular momentum, so it's spinning about an axis. So if you imagine, the nucleus of an atom being like a giant planet that's rotating, but just on a microscopic scale, then you should have theoretically these gravitomagnetic fields around the nuclei of the atoms. But they would only be around atoms with net nuclear spin, because, for example, an atom like carbon or sulfur, you have an equal number of protons and neutrons, so the net spin would be 0. So he talks about the importance of that. Well, my question for Ron was, how do you see that relating to, you talk about chirality and the Herkimer quartz and all that, and what concept is there a linkage between concepts here, or?
I want to, where was I? I guess, to Tim, you're familiar with the Wallace heat pump. He's a heat pump patent.
Yeah.
Okay, because what happened is after Wallace retired to Florida, he died, and he had a brother. It was called War Associates out in Colorado, and the only interest, they had strong interest from the Germans in the heat pump patent. So in terms of materials, when you're dealing with metals, I think you're better off. It's hard to say. It's just one thing I want to mention before I forget: bismuth. Bismuth is heavier than copper. So in terms of being one of his materials, bismuth and mercury from the Vimana, and bismuth is legendary. Also, in terms of my research, that may be helpful. Is anybody familiar with the bismanol magnet? It's called bismanol, B-I-S-M-A-N-O-L magnet. It's made from two materials. It's made from bismuth and manganese. These are two materials that should not be magnetic. When you put them together as an alloy, they become magnetic. It was invented by the U.S. Naval Department of Mines. It's a material that somebody should look into. In terms of metals, I don't really get involved in metals. Herkimer quartz, by being alpha and beta quartz, that interests me due to its chirality. If you type in chirality and space-time, you will get thousands upon thousands of hits. A lot of them are spurious. If you type in Kajome, K-A-J-O-M-E lattice, space-time, you'll get interesting hits on the nature of space-time as being related to triangles. So that's about as far as I can go here. So I won't use too much time. So that's, I see Mark has something. No?
No, this is bismuth. I cast it out of bismuth, basically.
Oh, yeah.
I'm not really sure what experiment I'll try with it. I think really what I want to do is melt it down and make it into plates and try that spinning experiment that he just talked about inside a laminar magnetic field.
I really think if you need to make it like a fine powder, because what I found is with bismuth, it's actually, as a solid piece, it doesn't attract much to a magnet, but when it's in a fine powder, it actually attracts to a magnet. So I think that the particles can orient themselves more freely when they're in a looser form, like a suspension.
Actually, bismuth is
it's diamagnetic.
Diamagnetic. It actually pushes away from magnets.
Yeah. Exactly.
No, it's actually magnetic. Well, I ground it down into a powder, some of the bismuth I had, and then I put a magnet near it, and sure enough, it was attracted to the magnet. Almost like iron filings.
That's very strange.
Yeah, totally.
That's why you can make the bismanol magnet. It was in operation until Alnico came. Alnico displaced the bismanol magnet. Bismanol had like a 3 or 4 year run.
Huh.
Oh, check this out. This is the diamagnetic effect with bismuth. You can see the magnet kind of floating there. Can you guys see that?
No. Got a flashlight from behind so you can see, because it's
so maybe in that solid form
I'm pretty sure everybody's seen it, but it's still entertaining. I mean, we threw that thing together. I went out to New Jersey to help Mark out with his gravity research projects, and we just kind of threw that thing together in an evening out of the fact that he had bismuth and apparently a metal smelting furnace sitting around for kicks, and there it is.
Yeah, can you see it floating? No, whatever, it's floating.
Ron, I had a question for you about these various materials. Now, in your patent, you talk about these this very strange material, which I believe is a liquid. Is that correct?
Oh, no. With the electrets, you have to be solid form.
We've had a lot of problems making electrets, and I'll tell you what, in all honesty, we could use a lot of advice because it's been a tremendous disaster trying to make them and failure after failure.
I've been with electrets for 23 years. You have to watch out for something called eutectic. When you mix certain benzochlorine materials together, even though they have melting temperatures of over 150 degrees, I'll use the word Fahrenheit, when you put them together at room temperature,
Is this like the drop of aluminum on a plate of, a drop of mercury on a plate of aluminum? Kind of the amalgam that it forms and the eutectic or whatever?
What he's referring to is that with these different dielectrics, when you're forming
I'm offline here somehow.
Go ahead, sorry, you're on.
No, you're online.
No, you just stopped talking.
Anyhow,
See you here.
I'm at Zoom sign up. I might log out and come back in. Hold on.
We can hear you, Ron, just so you know.
Ron, we can see you and hear you.
Okay, because all I have is a Zoom screen. What I want to say about
if you want to come back and try to log back in to get your
Hold on 1 minute. I can come back here. Hold on.
Okay, wait.
I'm going to my email.
Okay.
I am at email.
Well, Ron, let me mute you for just a sec.